welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about potential energy diagrams. Our aim for today is how can we extract information from potential energy diagrams. Before we get started, there's some definitions that we should talk about. The first one is system. The system is the part of the universe in which you focus your attention on. So if you're performing a chemical reaction in a beaker, the system would be that beaker. Whereas the surroundings would be everything else, the area surrounding that beaker, everything else in the universe. And the universe is the system plus the surroundings. Remember, according to the law of conservation of energy, energy cannot be created or destroyed. So, for example, if energy is being lost by the system, if the beaker is creating energy, the energy is being lost to the surroundings. The opposite is true as well. If the system is gaining energy, it is coming from the surroundings, the area around that beaker. The first process is an endothermic process. An endothermic process is one that absorbs heat from the surroundings. The prefix endo, meaning inside, it's taking in heat from the surroundings. Pretend that you have an ice cube in your hand. It feels cold to you because the ice cube is absorbing the heat from your hand. It's taking in heat from your hand. The ice cube is absorbing the heat. In an endothermic process, the system gains heat as the surroundings cool down. The ice cube is the system gaining heat. The surroundings, your hand, is cooling down. That's why it feels cool. And remember, heat flowing into a system from the surroundings is defined as positive. So that means a positive delta H value is taking heat in. Let's take a look at an example of an endothermic process now. On the left, we have a beaker with 200 milliliters of water at 37 degrees Celsius. On the right, we have 0.10 moles of potassium nitrate, KNO3. I am going to mix the potassium nitrate into the water, and then I'm going to put this video on time lapse to see what happens to the temperature. We're already at 35 degrees Celsius. Our final temperature is 30.5 degrees Celsius. Remember, we started off at 37 degrees Celsius, so our temperature went down by 6.5 degrees Celsius, an endothermic reaction which caused the surroundings to get colder. On the opposite side, we have an exothermic process. An exothermic process is one that releases heat into the surroundings. So the prefix exo, like to exit, heat is leaving the system. So in an exothermic process, the system loses heat to the surroundings. It feels hot. Pretend that you were to put your hand on a stove that is on. Don't do it, but pretend. If you had your hand on a stove that was on, it's going to feel hot to you. The stove is giving off heat. It's releasing heat into the surroundings. Your hand is absorbing the heat from the stove, so it feels hot to you. And finally, heat flowing out of a system into the surroundings is defined as negative. So you have a negative delta H value. Let's take a look at an exothermic process now. On the left, we have a 200 milliliter beaker of water at 34 degrees Celsius. On the right, we have 0.10 moles of sodium hydroxide, NaOH. Let's see what happens when I place the sodium hydroxide into the water and stir. I will then place the video on time lapse. Right now, we're already at 36 degrees Celsius, and rising. Our final temperature is 38 degrees Celsius. Remember, our initial temperature was 34 degrees Celsius, so the temperature rose 4 degrees Celsius, an exothermic reaction in which heat was released to the water. Here we have an exothermic potential energy diagram. On the x-axis, we have time. That could be in minutes, seconds, hours, doesn't matter. On the y-axis, we have potential energy. That is measured in kilojoules. And on this diagram, we have certain letters. We'll go through each one. The first one, letter A, is the potential energy, or PE, of reactants. That's the total energy of all of the reactants. If you see potential energy, that means the arrow is going to touch the x-axis. Letter B is the activation energy. That is the amount of energy required to activate or to start the chemical reaction. Think back to when we talked about pushing a car up a hill. In order to push that car over the hill and get it to the product side, to D, your destination, you have to give that car enough energy to get to the top of the peak and a little bit more to push it over. Then it'll roll down on its own. If you don't give the car enough energy, nothing's going to happen. It's going to roll back down to the starting point. Same thing with a chemical reaction. You need to give it the proper amount of activation energy to get it to the top of the peak and have it come down and form products. I'm going to skip C for a second and go right to D. D is the potential energy touching the bottom of the products. So nice and easy, it's the total amount of energy of all of the products. Which brings us to point C. Point C is known as either the heat of reaction or delta H. That's the change in energy of this particular reaction. So if I was just to give this graph, this y-axis, random numbers, so if I did 0, 5, 10, 15, and 20, 25, remember all in kilojoules. So we have delta H equals the potential energy of the products minus the potential energy of the reactants. The potential energy of the products, looking on the graph, is 5 kilojoules. Minus the potential energy of the reactants, which is 15 kilojoules. When I subtract 5 minus 15, I get negative 10 kilojoules. And that negative tells me it is an exothermic reaction. The negative delta H tells me that this reaction is releasing energy. That means that the products have less energy than the reactants. In this equation, we are losing heat. And the final letter, which is not drawn on here, so we'll draw it ourselves, goes from the top of the peak all the way down to the x-axis. That is our activated complex. The activated complex is the maximum amount of energy in this reaction. So that is the intermediate point in between the reactants and the products. When we talked about pushing the car up the hill, we need to get to the top of the activated complex. All the molecules have broken apart, and now they're going to reform into a more stable product. So to copy down those definitions, letter A was potential energy of the reactants, or PE of reactants. And that's the combined amount of energy for all the reactants. Letter B was the activation energy, so going up that peak. That's the amount of energy required to form the activated complex, the energy required to start that reaction. Letter C was the important one. That was your delta H. That's why we're doing these potential energy diagrams, to see if it's an endothermic reaction or an exothermic reaction, and how much energy is gained or lost. So heat of reaction is the amount of energy given off or absorbed, because it's endothermic, in the reaction. Remember, your formula is delta H equals potential energy of products minus potential energy of reactants. Products minus reactants, that will give you your delta H value. If it's positive, it is endothermic. If it is negative, it is exothermic. D, the potential energy of the products, or once again, PE of products. And that's the combined amount of energy for all of the products. And letter E, we had to draw in our cells. That's the activated complex. Intermediate state formed during the conversion of reactants to products. Remember, that's the maximum amount of energy, the tip of that peak in any potential energy diagram. Here are some notes about the activation complex. The activated complex occurs when reactants collide with proper speed and orientation. The bonds are in the process of breaking and forming. Remember the four letters BARF. Breaking, bonds, absorbs energy, and you release energy when forming new bonds. Every chemical reaction has BARF. They break bonds. How do they do that? They must absorb energy, and they release energy when they form new bonds. BARF. The activated complex is very, very unstable, only lasts for a brief moment, and then the reactants at the activated complex quickly move into a more stable product. Here we have an endothermic potential energy diagram. Similarly, we have time on the x-axis. On the y-axis, we have potential energy in kilojoules. And here, instead of letters, we have numbers. But number one is the potential energy of the reactants. Which is all of the energy combined of all of the reactants. Two is the activation energy. So that's the energy required to initiate the chemical reaction to get us to the top of the peak. Number three is delta H, which brings us to point four. Point four is the potential energy of products. And here, once again, we find delta H by subtracting products minus reactants. So once again, if I were to give random numbers, 0, 5, 10, 15, 20, and then 25 kilojoules up here, this time if I do products minus reactants, so delta H equals PE of the products minus PE of reactants. This time I do 15 kilojoules for my products minus 10 kilojoules for my reactants. 15 minus 10 is going to give me 5 kilojoules, a positive 5 kilojoules, which tells me that this is an endothermic reaction because energy was absorbed during this chemical reaction. The products have more energy than the reactants. And finally, also not drawn here, Number 5 is our activated complex. Once again, that goes from the tippy top of the peak all the way to the x-axis, and that is our activated complex. The maximum amount of energy in this reaction, our unstable point here, when our reactants are broken apart and they're about to momentarily going to reform into more stable products. Let's take a look at what happens when you add a catalyst to a chemical reaction. Remember, a catalyst lowers the activation energy for a chemical reaction, or, as the regents would say, provides an alternative energy pathway. So the normal pathway, represented by the solid line, is here. If you add a catalyst, you're lowering the activation energy. So you would represent a catalyst by drawing a dotted line inside the hump for the normal chemical reaction. A catalyst does not affect the reactants, and it does not affect the products. It lowers the activation energy and thereby lowering the activated complex. Here are some notes about catalysts. A catalyst is any compound that lowers activation energy, or as the regent says, provides an alternative energy pathway. A catalyst is not permanently changed in a reaction. A catalyst can be reused over and over again in subsequent chemical reactions because it's not changed. It's not used up in a chemical reaction. And finally, a catalyst does not change the heat of reaction, does not change the delta H value. So in our previous example, when we had our endothermic reaction, we did 15 kilojoules minus 10 kilojoules equals 5 kilojoules, that would still be the same. The only thing that would change in that last reaction, if we added a catalyst, would be to lower that peak, lower that activation energy, lower the energy required to start, to initiate that chemical reaction. So also, if the activation energy is lower, then the activated complex would be a little bit lower too. That was our dotted line in our last slide. And finally, all reactions are reversible. Here we have an exothermic chemical reaction. So we have the reactants, the activation energy, the energy of activation for forward, and then we have the energy of the products. In the middle we have delta H. So the forward reaction is exothermic. If we were to put just random numbers again, 0, 5, 10, 15, all in kilojoules, we do the delta H for the forward reaction, we would do products, which is 5 kilojoules, minus reactants, we would get 10 kilojoules. 5 minus 10 is negative 5 kilojoules. That's our forward reaction. And it's negative, which means it's exothermic, as we said before. However, if we were to reverse this reaction, the reactants become the products become the reactants. We would do this reaction backwards. In a reverse reaction, we would start here. Here we would have our reactants. This would be our activation energy. And then we'd have the peak, and we'd come back down to the products. So if we do the reverse reaction, the delta H, we would do the products, which were originally the reactants. We'd have 10 kilojoules minus the reactants, which were the products in the forward reaction, minus 5 kilojoules. And then we have a positive 5 kilojoules as our delta H. So our delta H, once again, does not change. In magnitude, it's still 5 and 5. The only thing that changes is the sign. If the forward reaction is an exothermic reaction, the reverse reaction must be an endothermic reaction. Finally, let's take a look at the activation energy. The activation energy for the forward reaction is from 10 from the reactants up into the peak. So the activation energy of the forward reaction is 15 minus 10, 5 kilojoules. The reverse reaction, we start here at 5, and we go to the top of the peak, which is 15. So 15 minus 5, the activation of the reverse, (15 minus 5 is 10 kilojoules. Here are some notes about reversible chemical reactions. Remember, in a reversible chemical reaction, the forward reaction is going to be opposite of the reverse reaction. Like in our last example, the forward reaction was an exothermic reaction. The reverse reaction was an endothermic reaction, opposites of each other. We figured that out by looking at the delta H values. When we found delta H for the forward reaction, we got a negative 5 kilojoule value. The negative meaning it's an exothermic reaction. When we did the delta H calculation for the reverse reaction, we got a positive 5 kilojoule delta H value. The positive meaning an endothermic reaction. And remember that the activation energy of the forward reaction is going to be different from the activation energy of the reverse reaction. What's the difference between the two? Well, that's going to be the value of delta H. That'll be the difference between the two activation energies, the value of delta H. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned how to label exothermic potential energy diagrams and endothermic potential energy diagrams. We learned about the 5 main parts of a potential energy diagram: the potential energy of reactants, the activation energy, the delta H or heat of reaction, the potential energy of products, and the activated complex. We also learned how to calculate delta H values, and we saw what would happen if we were to reverse a chemical reaction. Thank you again for joining us. I hope you learned something today. Please join us again soon. Bye.